Assalamu alaikum. My name is Khadija Mansoor and my topic of presentation is ultra high temperature ceramic. First, we will discuss the introduction of ultra high temperature ceramics. Let me start with the problem we are trying to solve. Material used in hypersonic flight, atmospheric re-entry, advanced propulsion, concentrated solar receiver, and the fuel system are exposed to some of the most extreme conditions engineered material can face. We are talking about temperature exceeding 2000 degrees Celsius combined with high mechanical stresses, severely oxidizing, and a corrosive environment, all acting simultaneously. Most conventional ceramic metals simply fail under this combination. That's where ultra high temperature ceramics come in. Ultra high temperature ceramics, such as the transition metal carbide like tantalum carbide, hafnium carbide, zirconium carbide, diboride like zirconium boride, are the hafnium diboride, carbonitride, and more recently, high entropy ultra high temperature ceramics are leading candidate because they combine exceptionally high melting point, very high elastic moduli, and the better thermal transport than oxide ceramics. This combination is rare. However, high melting point alone is not enough. Current research is therefore focused on four main directions. First is the composition expansion, especially high entropy and the carbonitride system to slow down the diffusion, suppress the phase instability, and improve the thermal and the chemical properties. Second is the advanced densification routes, such as ultra fast high temperature sintering, which dramatically reduce the processing time, grain growth, while cutting energy consumption. Third is the microstructure engineering, including the porous and dual phase high entropy architecture, which deliberately decouple density from thermal conductivity, that is critical for thermal protection and ablation application. And finally, machine learning and AI driven design, which are now begin used to optimize the composition, processing, parameter, oxidation, ablation resistance for more efficiently than the trial and error approaches. Together, these advances are transforming UHTCs from laboratory curiosities into the realistic engineering material with growing relevance for next generation aerospace, energy, and the extreme environmental system. Now we will study the chemistry and the crystal structures. So let's start with the chemical bonding. Ultra high temperature ceramic exhibit a high hybrid bonding framework dominated by the strong covalent metal non-metal bond between early transition metals light elements such as carbon, boron, and the nitrogen. This covalent bonding is supplemented by the partial ionic character and the metallic metal-metal interaction, creating a balance between stiffness and the transport properties. The strong directional covalency suppress the atomic diffusion, maintain the mechanical rigidity at extreme temperatures, while partial d-band occupations enable the moderate electrical and the thermal conductivity, unlike the conventional oxide ceramics. So, when we talk about the electronic structure, the density functional theory calculation reveals the pseudo gap in the electronic density of state near the Fermi level for many ultra high temperature ceramics. These pseudo gaps indicate the covalent stabilization and the correlate strongly with the high melting temperature and the thermodynamic stability. This electronic structure explains why ultra high temperature ceramics retain the stiffness and the phase stability even near the 3000 degrees Celsius. Now we will discuss the carbides. The carbides are the transition metals such as the zirconium carbide, hafnium carbide, tantalum carbide crystallize in a cubic NaCl type structure with the metal atom forming a FCC lattice and the carbon occupy octahedral sites that are the interstitial site on the FCC type of structure. This structure produces a isotropic three-dimensional bonding leading to the extremely high hardness melting point, hafnium carbide approaching the 3950 degrees Celsius in nearly stoichiometric composition. However, carbon vacancies are common and strongly influence the thermal conductivity, phonon scattering, and the high temperature creep behavior. Second one is the transition metal nitride. The transition metal nitride form a relative ultra high temperature ceramic subclass with a melting temperature above 3000 degrees Celsius, high elastic moduli, and the mixed covalent and the ionic bonding. Compared with the carbide, nitride generally show the high thermal and electrical conductivity and improving the thermal shock resistance. Their key limitation is poor oxidation resistance above 1000 to 1200 degrees Celsius, so they are typically used in composite are the multi-phase ultra-high temperature ceramics. Densification of the nitride containing ultra-high temperature ceramics require advanced processing method due to the extremely low self-diffusion. Next is the carbon nitride and the emerging phase mixed anion system like the hafnium carbon nitride allow tuning of bonding and the defect chemistry. High throughput DFT and the machine learning studies have predicted layered carbide and the nitrided phases with the high thermal stability. However, most of these remain computational prediction and require the experimental validations. The other class is the diborides. The diborides include the zirconium boride, hafnium diboride, adopt a hexagonal AlB2 type of structures consisting of rich boron honeycomb layer separated by the metal plane. Strong boron-boron covalent bonding result in very high in-plane stiffness and extropic thermal transport, while the metallic layer enhance the electronic conductivity. The AlB2 type of structure of diboride can be clearly seen in that figure. Next are the high entropy, ultra high temperature ceramics. High entropy ultra high temperature ceramics incorporate the multiple metal cation on a single sublattice, increasing their configuration and entropy their disorder. This leads to the lattice distortion, suppressed diffusion, and improves phase stability, which can enhance oxidation resistance, grain growth control, and despite their promises, the processing and the phase stability window remain challenging in the high entropy ultra high temperature ceramics. Let's move toward the reaction mechanism and the chemicals pathway. First are the carbothermal reduction, carbide formation. Carbothermal reduction mechanism is that the carbothermal reduction is a primary synthesis route for the transition metal carbide from oxide at ultra high temperature. The process begins with the adsorption of carbon, either solid carbon or a carbon derived from the precursors onto the surface of metal oxide particles. At elevated temperature, carbon extracts oxygen from metal oxygen lattice and producing the carbon monoxide gas. This remover of the oxygen reduce the metal cation, enabling the formation of metal carbon bonds and reduce the metal atoms, then diffuse locally and react with the available carbon to form the carbide nuclei. As the reaction progresses, these nuclei grow through solid state diffusion and the surface reaction. Simultaneously, carbon monoxide gas evolve and escape. If gas evolution is too rapid or diffusion is limited, residual porosity can remain and making atmosphere control and heating rate critical. The overall reaction can be summarized by that reaction, that is M metal oxygen plus the carbon, so that the oxygen will be eliminated and metal react with carbon and it will form the metal plus non-metal bond, while that the carbon and the oxygen will be eliminated as a carbon monoxide gas. Next is the borothermal pathway for the formation of the diboride formations. So, metal diboride are commonly synthesized via the borothermal or the borocarbothermal reduction, typically using the boron carbide as a boron source. Initially, the metal oxide reacts with the boron to form the diboride nuclei, while oxygen is liberated from the oxide lattice. Because boron alone is insufficient to fully remove oxygen, excessive carbon play a critical role in that case, and, and oxygen will be removed as a carbon monoxide gas. At high temperature, transient boron-rich liquid phase may form and significantly enhancing the mass transport. This liquid prompt promote rapid diffusion and the grain rearrangement and the densification of the diboride phase. The final result is dense Mb2 grain with the carbon monoxide as a primary gaseous byproduct, and the overall reaction will be that the metal oxide plus boron carbide plus carbon, so that the metal will be react with the diboride and the carbon monoxide will be eliminated as a byproduct. This pathway explains why diboride processing is more sensitive to carbon balance and temperature control than that of the carbide synthesis. Now we will move toward the reactive routes for the high anisotropic composite ultra high temperature ceramics and the reactive and the sequential processing. For high entropy, ultra high temperature ceramics and the multi-phase composites, simply single step reduction is often insufficient. Instead, mechanical alloying is used to homogenize multiple metal oxide followed by the stage carbothermal and a porothermal reaction. Thermodynamically, carbide and boride are strongly favored at high temperature due to their large negative Gibbs free energy of formation. However, densification is largely kinetically controlled. Transient or tactic are a liquid phase accelerate diffusion and the reaction rate. Ultra-fast sintering techniques such as ultra-high heating rate exfoliate this kinetic effect to achieve near full density before excessive grain growth occur. After studying the different types, now let's move toward the engineering synthesis and the fabrication. First are the conventional processing technique, hot pressing and the spark plasma sintering. Hot pressing and the spark plasma sintering are the most established densification route for the ultra high temperature ceramics. Both methods apply simultaneous pressure and a high temperature, enabling high relative densities and the fine microstructure. The spark plasma sintering significantly reduces the processing time due to the rapid joule heating and enhanced diffusion. However, it is energy intensive, expensive, and suffer from limited scalability for large or complex components. In addition, the rapid heating can introduce a non-equilibrium defect which may affect the high temperature stability. Second is the combustion synthesis. Self propagating high temperature synthesis is an efficient route for producing ultra high temperature ceramics powders through highly exothermic reactions. While SHAs offer low external energy input and rapid synthesis, the resulting products are typically porous, inhomogeneous, and require subsequent densification steps such as hot pressing SPS for structured applications. That were are the conventional methods. Now we will see to now move toward the emerging methods, emerging and advanced processing methods. Ultra fast high temperature sintering. Ultra fast high temperature sintering employs extremely rapid thermal cycles, often on the order of seconds to minutes. These conditions promote the formation of transient or tactic or liquid phase, which dramatically enhance their diffusion and allow near full densification while suppressing the excessive grain growth. Recent studies demonstrate an entropy stabilized diboride composite processed by UHS achieving 90% relative density and nano hardness value approaching 27 GPa, highlighting its potential for advanced ultra high temperature ceramics. Next is the reactive additive manufacturing. Reactive additive manufacturing involves printing oxide or polymer drive green bodies which are subsequently converted into carbide, boride, while carbothermal are the borothermal reactions. Although still at an early development stage, reactive AM offer a unique advantages. First, the ability to fabricate complex and graded geometries that are extremely difficult to achieve through a conventional sintering route. Second one are the high entropy sequential synthesis. High entropy sequential synthesis required engineered precursors, chemistry, staged reduction pathways to achieve the homogeneous solid solution. Sequential synthesis allow control over phase formation, enabling the production of single phase high entropy ceramic or dual phase microstructure with the tailored thermomechanical properties. The process control consideration that we should be keep in mind involve the successful UHT fabrication critically depend upon process control. It included inert or mildly reducing atmosphere to suppress the oxidation and volatilization, precise carbon and boron stoichiometry to avoid the residual oxygen or free carbon, optimize heating profile to balance densification and grain growth, protective coating or sacrificial layer to limit the surface degradation during the processing. So these were some fabrication and the synthesis route for the ultra high temperature ceramics. Now we will move towards the properties. First are the mechanical properties, hardness, and the elastic response. Ultra high temperature ceramics exhibit the exceptionally high hardness, stiffness due to the strong covalent metal non-metal bonding and the dense crystal lattice. For example, hafnium carbide show the weaker hardness in the range of 20 to 30 GPa, while zirconium carbide is slightly lower 18 to 26 GPa. This hardness originates from the directional covalent bonding which strongly resists the dislocation motion. Elastic moduli typically exceed the 400 GPa. In diboride, the AlB2 type layered structure lead to the pronounced elastic anisotropy. Stiffness is significantly higher in the basal plane than along the C axis, reflecting strong in plane BB bonding. Next is a fractional toughness. Despite their strength, monolithic carbide and the borides suffer from low fractional toughness, typically range from 3 to 5. This brittleness arises from limited plasticity and the absence of effective crack bridging mechanisms. Tuffing can be enhanced by the composite architectures. Mixers are the particle reinforcement high entropy solid solutions. This approach impedes the crack propagation through crack deflection, grain bounding, strengthening, and the stress redistribution. Next is the creep and the fatigue at the high temperature. High temperature creep and fatigue are strongly stress and temperature dependent, governed primarily by the diffusion controlled mechanism. High entropy and drop ultra high temperature ceramics show reduced creep rate due to the lattice distortion, vacancy suppression, slower atomic diffusion. As a result, this system maintain dimensional stability under prolonged thermomechanical loading, which is critical for the hypersonic and the re-entry environment. Next is the thermal properties, thermal conductivity and anisotropic. Diborides such as zirconium boride, hafnium boride exhibit relatively high thermal conductivity and they depend upon the purity, porosity and the defect concentration. Their layered crystal structure produce anisotropic heat transport with higher conductivity in the basal plane than along the C axis. Defects, vacancies, porosity increase the phonon scattering and reducing the thermal transport efficiency. Next is the coefficient of thermal expansion is a critical parameter for coating compatibility and the structure integrity. Carbide are generally more isotopic. Diboride show moderate anisotropic and CTE mismatch between ultra high temperature ceramics and substrate or coatings can generate the severe thermal stress during heating and the cooling cycle. The specific heat and the thermal diffusibility govern the transient metal response, while the strong bonding yield the moderate heat capacities and the defect induced phonon scattering reduce the diffusibility, directly impacting the thermal protection system and the performance. The next is the microstructure. The microstructure's properties, relationships that involve the grain size, phase, and the porosity. Microstructures strongly dictate performance. Fine, homogeneous grain enhance hardness, suppress the crack initiate, while the coarse grain may improve the toughness, while the micro crack deflections. Dual phase and the composite system balance strength, toughness, and the thermal conductivity. Porosity reduces the modulus conductivity but can improve the thermal shock resistance in the ablative and the insulating components. Next are the high entropy and the layered structures. In high entropy, ultra high temperature ceramics, lattice distortion inhibit the diffusion, improve the creep resistance and the oxidation stability. Layered carbide and nitride enable the directional thermal transport, allowing the engineered anisotropy for the target high temperatures applications. Next is their representative single phase properties, processing dependent. There is a reported range. Melting point for hafnium carbide is 3950 degree and their hardness is 2030 GPa. Melting point for zirconium is 3400 and the hardness is 18 to 26 GPa. While that for the borides, their melting point is 3000 to 3250 degrees Celsius. Their thermal conductivity range from 50 to 120 and hardness 18 to 25 GPa. Now we will see the composite effect and their design. Composite optimization in zirconium boride silicon carbide composite silicon carbide addition 10 to 30% volume improve the oxidation resistance by forming a protective silica oxide glass scale. However, excessive silica carbide can degrade the high temperature strength. Machine learning approaches are increasingly used to identify the optimal composition window for specific thermal and the flux conditions. High entropy porous ultra high temperature ceramics exhibit a very low density and the thermal conductivity, making them suitable for insulation or ablative roles rather than the load bearing component. Ultra high temperature ceramic designs is a multi objective optimization problem that we have to see strength vs their toughness, oxidation resistance, and their thermal conductivity, density, and their thermal protection. These trade offs are resolved through composition, microstructures, and processing control, increasingly guiding by the data driven and ML approaches. The next is the oxidation, ablation, and the protection. Oxidation behavior is often the ultimate performance limiter. Carbide oxidize to form the carbon monoxide, where the carbon monoxide is volatile. Boride form the boride oxide gas, which is viscous but volatile at very high temperature. The silica carbide addition generally silicon oxide protective scales, while rare earth dopant increase the scale viscosity and the adherence. Multi-phase and the graded ultra-high temperature ceramics exfoliate the sacrificial outer layer while protecting the load-bearing core. Next is the machine learning and the AI for the ultra-high temperature ceramics. Their data and the feature engineering. Modern ultra high temperature ceramics design increasingly relies on the data driven approaches to complement the experiment and DFT predictions. The key data sources include the experimental databases, composition, sintering condition, microstructure, measured properties, DFT outputs. There is a formation, enthalpy, phonon, stability, elastic constant, and the process metabase, that is their temperature profile, atmosphere, precursors, type, etc. The crucial descriptor that we feed in our machine learning for the synthesis and the design of our ultra high temperature ceramics are as follows. The descriptor involves the electronegativity difference symbol is delta S, and it is a difference in electronegativity between the metals and the non-metals, and it affects the bond strength, oxidation resistance, and the thermal stability of our ultra high temperature ceramics. Next are the valence electron concentrations, that is represented by the VEC electron per. These are the average number of valence electron per atoms influence the electronic structure, hardness, and the elastic moduli of our ultra high temperature ceramics. Other is the formation enthalpy, that is the energy change during the formation from the elemental constituent. It indicates the phase stability and the tendency for the decomposition. Atomic radius, that is the ratio of atomic radii, fraction of unit cell volume occupied, influence the lattice distortion, thermal expansion, and the mechanical properties. Other is the vacancy formation energy. It is the energy required to create a point vacancy. It controls the diffusion rate, creep resistance, and the thermal conductivity. Elastic constant, that tells about the stiffness component from DFTR experiment. It predicts the mechanical behavior, anisotropy, and the fracture toughness. Density mass per unit volume, it is relevant for the thermal conductivity, heat capacity, and TPS design. Bond length and coordination, average metal non metal bond distance, and the coordination number correlate with the hardness, melting point, and the thermal expansion of the ultra high temperature ceramics. Phonon stability, that is the maximum or minimum phonon frequency from DFT, and it predicts the thermal conductivity, dynamic stability, and the high temperature performances. So these are some descriptors that we feed in our machine learning. Now we will move toward the models and the workflows. The supervised machine learning models such as the random forest, RF, sport vector regression, SVR, and the neural network are widely used to predict oxidation rate, hardness, thermal and electrical conductivities. Active learning and the Bayesian optimization prioritize experiment that maximize information gain, reducing the number of costly high temperature synthesis. ML interatomic potential accelerate the large scale property prediction that are elasticity phonons for candidate composition, far beyond what DFT alone can achieve. Their workflow overview is that the typical ML driven design loop is a dataset curation, experimental plus computation data, descriptor engineering, convert chemical and the structural feature into the ML ready input, model training and the uncertainty quantification, acquisition selection, identify the most informative experiment or composition, experimental validation, that is the synthesis and the test candidate. Data set update include the incorporate new result to improve our models. So these are some workflow for our machine learning that we operate in our model to improve the design of the ultra high temperatures. Now we will see what will be their representative outcomes. So, zirconium boride silicon carbide composites, the ML predict the optimal silicon carbide fraction to form the protective silicon oxide glass scales while maintaining the mechanical strength, achieving the R2 0.8 to 0.9 on curated test scales. The layered carbide and nitride combined DFT plus ML screening proposed dozen of candidate phase with the predictive TM2500K ready for experimental validations. These examples demonstrate that ML accelerate discovery, identify composition, property relationship, and help navigate the vast UHT design space much faster than trial and error experiments. So, machine learning in UHTCs is not just about prediction, it is to design tools linking bonding structure processing to high temperature performance. By combining the computational machine learning and the experiment, researcher can reduce the trial and error effort, optimize the multiple objective properties, and explore the complex systems like high entropy and the layered ultra high temperature ceramics and the high entropy composites. Now we will discuss the engineering application of the ultra high temperature ceramics. First is a hypersonic leading edge and the thermal protection systems. So what will be their performance involved? The transient surface temperature up to 2000 to 2500 degrees Celsius, heat flux in the MW dot M minus per minus 2 range. Material must resist resections, retain their stiffness, and withstand the oxidation ablation. So these are the requirement that is required in a hypersonic leading edge. So the integration strategies, the leading edge and nose tips made from the zirconium diboride silicon carbide and the hafnium carbide composite. Use of graded coating to manage the oxidation and the thermal expansion. The compliant substrates to reduce the thermal stress. Optional active cooling for the for extended missions, and the sacrificial layer suffix for the short duration flight. This figure showed that where we use the ultra high temperature ceramics, and the hot red part showed that where it can bear the maximum heating temperatures. So next we will study the energy system, concentrated solar system, and the nuclear, where the ultra high temperature ceramics are used. Ultra high temperature ceramics allow receiver to reach the higher temperature, improving the thermodynamic cycle efficiency. And the fusion reactor ultra high temperature ceramics in them under evolution for plasma facing and the high temperature structural component. And the key concern are the neutron irradiation tolerance, long term Korean, and the thermomechanical reliability. Lightweight insulation and ablators. The porous high entropy ultra high temperature ceramics provide the ultra light thermal insulation with the usable compressive strength, ideal for the low mass TPS panels or thermal insulation insert where the structural loads are the moderate. We can also use the ultra high temperature ceramics in the medical tool and the instrumentation. Physical application where they can be used are the sterilizable cutting tapes, wear resistance coating, and the radiation hard operators. Not feasible where we cannot use them without engineering are the monolithic implant due to their low toughness, iron release concern, and the uncertain biointegration, so that their compliance with the ISO 10993 and GLP testing is mandatory for any biomedical development. So they have to be compared with that, passed through that testing before they're used in a medical field. Now we will link the ultra high temperature ceramics with the SDGs. The SDG 7 is the affordable and the clean energy. SDG 7 focus on ensuring the access to affordable, reliable and sustainable and the modern energies. Ultra high temperature ceramics contribute to this goal by enabling energy system to operate at significantly higher temperature than the conventional materials. In concentrated solar power plant and the next generation nuclear and the fuel reactor, efficiency increases as the operating temperature increase. UHTCs retain mechanical strength, oxidation resistance, and the thermal stability at temperature where metal and the conventional ceramics fails. By allowing higher operating temperature, UHTCs improve thermodynamic efficiency, reduce energy losses, and lower the overall cost per unit of clean energy produces. This directly supports the transition away from the fossil fuels. Next is the SDG 9, that is the industry innovation and the infrastructure. SDG 9 emphasizes on the resilient infrastructure and the technological innovation. UHTs are critical enabler of advanced aerospace, hypersonic transport and the high temperature industrial system. In hypersonic vehicle and the reusable spacecraft, UHTCs withstand extreme aerodynamic heating and the mechanical stress. This durability allow for reusable system, reducing the material waste, launch cost while strengthening the technological infrastructure. Additionally, UHTCs support the innovation in industry process by enabling the cleaner, more efficient, high temperature manufacturing with the reduced contamination and the longer component life. SDG 11 is the sustainable cities and the communities. Although UHTCs are not used directly in everyday urban construction, they play a vital indirect role in the sustainable cities. UHTCs enable the durable satellite space vehicles that support the climate monitoring, weather forecasting, and the disaster management. These data system helps cities plan infrastructure response to extreme weather and event and improve public safety. By improving the resilience to climate related risk, UHTCs contribute to make the cities safer, more adaptive, and more sustainable. SDG 12 involve the responsible consumption and the production. It focuses on reducing the resource consumption and the waste, and it aligns strongly with the goal due to their exceptional durability and resistance to degradation. Because UHTCs resist creep, oxidation, and thermal shock, component last significantly longer. This reduces the frequency of replacement, lower raw material extraction, and decrease the waste generation over the system lifetime. In high performance application, a single UHTC component can replace the multiple low performance material, supporting more responsible the production practice. And the CHT 13 involve the climate action. UHTCs contribute to climate action primarily through the indirect emission reduction by enabling the high efficiency clean energy system, fuel efficiency propulsion, and reusable aerospace technologies. UHTCs help reduce the greenhouse gas emission over time. They also support the climate adaptation by enabling the technologies that operate reliably under extreme temperature, which are becoming more frequent due to the climate change. So, in the end, the full sustainability required the life cycle analysis and the low carbon sintering energy sources. Now we will move toward the future perspective and the roadmaps. AI experiment ecosystem, the federate UHTC's dataset plus the active learning to accelerate the discovery and optimize the oxidation toughness trade-offs. Then is a process intensification and the scale up, translating the UHS and the reactive AM to industrial scales while preserving our microstructure. Advanced coating and the functionally degraded composite that are FGCs, multi-scale testing, plus the ML kinetic model to design durable oxide scale under the cyclic thermal flux. And last one is our non-equimolar high entropy design. Expand the meta-stable composition space to tune the properties beyond the equimolar approach. Also, there are some the recommendation area where we need to be focused that are to improve the oxidation resistance. It will protect the coating and self-healing layers, mechanical and thermal shock to improve the toughness and the lightweight design For the porosity control, the manufacturing by using the additive sintering and the advanced sintering, the property control by focusing on the tunable thermal and electrical behavior, multifunction systems, modeling by the help of the AI and the predictive simulation and the application integration, that is the real system testing and the certification, that fields also need to be the focus. In the last, there is a conclusion for the ultra high temperature ceramics. The recent 2022 3 to 2025 advance in high entropy chemistries, UHS processing, porous dual phase architecture, ML guided optimization materially improve UHTC's prospect for the engineered deployment. Remaining major challenges are the oxidation protection, fracture toughness, scalable energy efficient manufacturing, and the integration chemical design and the processing science, and the AI tool is the fastest route to robust the developable UHTC systems. In the end, there is an abstract that is a summary of my whole presentation. The ultra high temperature ceramics are class of the advanced material that is distinguished by their exceptional thermomechanical and the chemical stability, making them ideal for the extreme environmental where the conventional ceramics fail. So, it involve the boride, carbide, nitrides, carbonitrides, and their composite. They have high hardness, high elastic moduli, which are outcome of the strong covalent metal non-metal bonding. We also discussed different fabrication techniques, their microstructure control, their oxidation and ablation behavior, also their practical application in aerospace, defense, biomedical field, and also we have studied their integration with the AI assisting material, their link with the sustainability goals, and this review synthesis current research to provide the comprehensive understanding of ultra high temperature ceramic, offering insight for the future innovation in ultra high temperature material, and it also highlight the gap in knowledge that require the further experimental and the computational investment. That were the some keywords from my presentation, and that were the reference that I used for my content, and that's all from my side. Thank you.